Good morning. In my previous video about parallel plate capacitors, we learned a little bit about vacuum permittivity and dielectric constants. Today, we're going to delve deeper into both of those concepts.
Flippin' physics.
As discussed previously, the capacitance of an ideal parallel plate capacitor with an insulating material, or a dielectric, between the two plates equals kappa, the dielectric constant of the dielectric which is between the two plates, times epsilon naught, the electric permittivity of free space, or vacuum permittivity, which has a constant value of 8.85 times 10 to the negative 12 coulombs squared over the quantity newtons times meter squared, times capital A, which is the area of one of the plates, all divided by lowercase d, which is the distance between the two parallel plates. Now, we've not really discussed what the electric permittivity of free space is, but we will soon. However, first, let's start with a parallel plate capacitor which does not have a dielectric placed between the plates. In other words, right now there is nothing. There is free space. There is a vacuum between the two plates. The dielectric of a vacuum is 1. So the capacitance of this capacitor equals vacuum permittivity times the area of one plate divided by the distance between the two plates. Okay, so right now, the electric field between the plates is labeled capital E naught, which represents the electric field before we place the dielectric between the two plates. Let's start by charging both plates to a charge of capital Q and disconnecting the capacitor so it is electrically isolated. In other words, no charges can flow to or from either plate.
If both plates are charged to a charge of capital Q, how can there be an electric field?
What do you mean?
If both plates are positive, I feel like there won't be a uniform electric field between the two plates.
Right. I think he means that both plates are charged to a charge of capital Q, and the positive plate has a charge of positive capital Q, and the negative plate has a charge of negative capital Q.
Okay, yeah, that makes more sense.
Right. Sorry. Yeah. Let's label the electric potential difference between the two plates as delta capital V naught, where that is the positive of the electric potential difference. And now let's add a dielectric between the two plates in red. Now, all dielectrics are made from insulating material. Bo, please explain what would happen if a dielectric were made of a conducting material instead.
Sure. If a dielectric were made of a conducting material instead of an insulating material, the conducting material between the two plates would allow charge to flow between the two plates, and the conductor would not be able to maintain a charge separation between the two plates. A conductor between the two plates would basically short circuit the capacitor, which would be something entirely different than a capacitor.
But could a dielectric be made from a semiconductor?
That is a fair question, Bobby. Semiconductors, which are materials with electrical conductivity somewhere between a conductor and an insulator, are not really a part of this curriculum. But yes, in highly specialized applications, sometimes semiconductors are used to make dielectrics. However, again, for our purposes, know that a conductor is never used as a dielectric because it would cause the charge to flow between the plates. And in this class, all dielectrics are made from insulating materials. Because the dielectric is an insulator, a material that does not allow electric charge to flow through it easily, charge does not flow through the insulator. Instead, what happens when the dielectric is added between the two plates is that the charged particles in the insulator become polarized. They arrange themselves such that the negative sides of the dielectric's charged particles are closer to the positive plate of the capacitor, and the positive sides of the dielectric's charged molecules are closer to the negative side of the negative plate of the capacitor. Clearly, this illustration is a highly idealized representation of the polarized molecules in the dielectric. However, it is still helpful for understanding what is happening here. And notice that the polarization of the ideal dielectric material induces a uniform electric field which is opposite the direction of E naught, the original electric field in the capacitor before the introduction of the dielectric. Again, the direction of the induced electric field in the dielectric, which is in blue in the illustration, goes from the positive to negative charge of the polarized molecules in the dielectric, which is opposite the direction of the original electric field between the parallel plates without a dielectric. Okay, now, what happens? Billy?
Okay, the original electric field E naught and the induced electric field in blue are opposite in direction, That means that the net electric field with the dielectric between the parallel plates is decreased from the original electric field E naught.
Correct, and I have updated the illustration to reflect that.
Thanks.
Yeah, now I can see why the electric field decreases with the addition of the dielectric.
Yeah, and because the electric field is uniform, we know the positive value of the electric potential difference equals the electric field times the distance between the plates. Because the electric field decreased and the distance between the plates did not change, the electric potential difference between the two plates also decreased. And because the capacitor is electrically isolated, the charge on the plates of the capacitor does not change, and capacitance equals charge over electric potential difference. Therefore, because the electric potential difference between the plates is in the denominator of the capacitance equation and the electric potential difference decreases, adding a dielectric between the two plates increases the capacitance of the capacitor.
Exactly. Adding a dielectric between the plates of an ideal parallel plate capacitor that is electrically isolated decreases the electric field, which decreases the electric potential difference, which increases the capacitance. Okay, now, the way we define the effect of a dielectric is with the dielectric constant. The symbol for the dielectric constant is the lowercase Greek letter kappa. It looks basically like a lowercase k. The dielectric constant equals the ratio of the electric permittivity of the dielectric, the epsilon symbol with no subscript, to the electric permittivity of free space or vacuum permittivity. Because the dielectric constant is a ratio of two electric permittivities with the same units, the dielectric constant has no units. And electric permittivity, epsilon, is the measurement of how much a material is polarized when it is placed in an electric field. The easier it is for electrons to change configuration in a material, the larger the dielectric constant of the material. And that brings us back to the equation for the capacitance of an ideal parallel plate capacitor with a dielectric between the two plates. Capacitance equals the dielectric constant times vacuum permittivity times the area of one plate divided by the distance between the two plates. But let's take some time to talk a bit more about electric permittivity, epsilon. Actually, could the three of you please talk more about electric permittivity?
Absolutely.
Okay, sure.
Electric permittivity is the measurement of how much a material is polarized when it is placed in an electric field.
And in an electrically isolated capacitor, the more the dielectric is polarized, the larger the induced electric field inside the dielectric, and therefore the smaller the net electric field between the plates of the capacitor.
And the smaller the net electric field in the capacitor, the smaller the electric potential difference between the plates of the capacitor, and therefore the larger the capacitance of the capacitor.
That means that the easier it is to polarize the molecules which make up the dielectric, the larger the dielectric constant, and the larger the capacitance of the capacitor.
Well done. Now, epsilon naught is the electric permittivity of free space or vacuum permittivity. I'm calling it epsilon naught so as not to confuse vacuum permittivity with capital E naught, the original electric field in the capacitor before the dielectric is added. Vacuum permittivity equals 8.85 times 10 to the negative 12 coulombs squared over the quantity newtons times meters squared.
What?
Yes. The vacuum of space has an electric permittivity.
Okay.
Sure.
Yes, the vacuum of space has measurable physical properties that affect how electric fields and electromagnetic waves behave. Space is not merely a void. It is characterized by the permittivity of free space, which defines the baseline for how electromagnetic fields propagate. Electromagnetic waves, which include visible light, travel through the vacuum of space. It is how we see the stars. Electromagnetic waves traveling through the vacuum of space is how we get energy from the sun, which is how we can survive on this planet. But okay, that is getting outside the scope of the curriculum for this class.
Yeah.
Yeah, we are.
Okay, back to the dielectric constant of a material, which equals the electric permittivity of the material divided by the electric permittivity of free space. That means the electric permittivity of the material equals the dielectric constant of the material times the electric permittivity of free space. Every dielectric material has an electric permittivity, and all of them are larger than the electric permittivity of free space. In other words, every dielectric constant is greater than 1 because every material will polarize at least a little bit in the presence of an electric field. except a vacuum, of course, because by definition, the dielectric constant of a vacuum equals exactly 1. Giving every material a dielectric constant makes it a bit easier to conceptualize how the dielectric compares to a vacuum. For example, take a look at this table of dielectric constants, which has values from a table on the Engineering Toolbox website. Let's determine the electric permittivity of Mylar. Mylar, in case you are unfamiliar with it, is a brand name for a specialized high-strength polyester film which is used in food packaging, emergency blankets, balloons, electrical insulation, architecture drawing, and capacitors. I am familiar with Mylar from my high school days. For example, this drawing of a toy car I disassembled is on Mylar paper. Yes, I have fond memories of putting mechanical pencil to Mylar paper in drafting classes.
Nice.
Wow.
You drew that by hand?
Okay.
Wow.
Actually, sorry. No, I did not actually draw this by hand. My school purchased a computer-aided design program for the first time during my junior year in high school, and I drew this in a program called VersaCAD, and then had the computer draw it on Mylar paper. Sadly, I was unable to locate any of my original hand-drawn drafting drawings from high school.
Well, it's still fun to see.
Thanks. Okay. Bobby, please determine the electric permittivity of Mylar.
Okay, from the table, we know the dielectric constant of Mylar equals 3.1, and the dielectric constant of a material equals the electric permittivity of the material over the electric permittivity of free space. That means the electric permittivity of Mylar equals the dielectric constant of Mylar times the electric permittivity of free space. That means the electric permittivity of Mylar equals 3.1 times 8.85 times 10 to the negative 12, which is 2.7435 times 10 to the negative 11, or with 2 sig figs, roughly 2.7 times 10 to the negative 11 Coulomb squared over the quantity newtons times meters squared.
Thank you, Bobby. Notice that because the dielectric constant of a vacuum is 1, it is a lot easier to recognize that the capacitance of a parallel plate capacitor with Mylar between the plates will have a capacitance that is 3.1 times larger than a similar capacitor without a Mylar dielectric. Then it is to compare those values by knowing the vacuum permittivity is 8.85 times 10 to the negative 12. The electric permittivity of Mylar is 2.7 times 10 to the negative 11. We do not have to use dielectric constants of materials. We could just use electric permittivities of the materials instead. However, using dielectric constants makes our lives just a little bit easier.
Okay.
Yeah.
Sure.
And lastly, just so you know, the electric permittivity of free space, or vacuum permittivity, appears in a large number of physical relationships. For example, the Coulomb constant can be given in terms of vacuum permittivity. The Coulomb constant equals 1 over the quantity 4 pi times vacuum permittivity. That means the electrostatic force can be given in terms of vacuum permittivity. And there are many examples we will not cover in this class, like Gauss's law, which states that the net electric flux through any closed surface, which is called a Gaussian surface, is directly proportional to the total net charge enclosed within that surface divided by the electric permittivity of free space. And the energy density of an electric field, and the speed of light, where mu naught is called vacuum permeability. But
what?
No, I'm not going to talk about all of these equations. I bring them up simply to point out that the electric permittivity of free space is a number which appears in a large number of physical relationships in physics. Okay, I think that is enough for today.
Yep.
Yeah. Thank you very much for learning with me today. I enjoyed learning with you.